Let's sit down with StreamNative's Sijie and Matteo Merli to discuss Ursa, cost-conscious data streaming for Kafka and beyond. I'd like to thank both of you for sitting down today for this discussion about Ursa and data streaming in the cost-conscious era that we're in. Just so viewers are aware, I'm Dustin Nest. I'm StreamNative's technical trainer. But obviously, our viewers are more interested in knowing more about you before we get into our discussion. So, CJ, if we could start with you, could you give our viewers a brief introduction of yourself?
Sure. Thank you, Dustin, and thank you for hosting this podcast. My name is Sijie Guo, co-founders and CEO of StreamNative, one of the co-creators of Pulsar, and work on data streaming for years. And very excited and to be here and talking about Ursa.
And Matteo, if I could also get you to give a brief introduction to our viewers.
Hey, thanks. My name is Matteo Merli, and I'm CTO in StreamNative, and I was one of the co-creators of Apache Pulsar, and I'm also the PMC chair of the Pulsar project.
Awesome. Thank you both again for being here. We could start the discussion with an understanding of the history of Kafka, Pulsar, how OSS Pulsar led to the creation of StreamNative. Basically, we could go into that full history. But what I really want to talk about today is Ursa. I would actually like to start instead with what is Ursa and what were its guiding principles. So maybe CJ, if you can give a quick introduction to what is Ursa and why is it so important for the streaming marketplace right now?
Sure. So at a very high level, Ursa is an enhanced version of Pulsar. It's actually built as a Kafka-compatible data streaming engine, built directly on Lakehouse, and we are able to kind of turn data stream into Lakehouse table and being able to share with an analytics process. And obviously, it's designed for a cost-conscious era that we believe it bring in this cost efficiency to most of the people and most of the organizations. And most important thing I want to emphasize, it's Kafka API compatible, which is beyond just Pulsar.
Okay. And I was about to say one thing you left out, but you did just add it in, was the Kafka protocol. And that does seem like one of the guiding principles for Ursa is its complete support for the Kafka protocol. Matteo, could you elaborate more on the support and why it was so important to include this as one of the key features of Ursa?
Sure. I mean, there are multiple reasons, right? First of all, is that you have to recognize that the Kafka protocol has been becoming ubiquitous. There are like so many applications already built with this, with the assumption of Kafka protocol, and there is a lot of differentiator in the market for like a different Kafka implementations. There is not just one Kafka implementation anymore. And second is that our platform is a messaging streaming platform. So its main purpose is to communicate with and integrate with multiple different systems, and we need to be able to speak all the languages, right? So and Kafka protocol being one of the most used languages, then out there, it is imperative for us to have a first class support such that you can like have 100% compatibility within the StreamNative platform with the Ursa engine with all your Kafka applications and other external third-party partner systems that are using and are expecting Kafka protocol.
So it seems like if you wanted to summarize Ursa for our viewers, key features of it are the Lakehouse storage and the Kafka protocol. And CJ, if I could get you to elaborate on Lakehouse storage just a little bit more.
Lakehouse, I mean, we commonly see like the destination of a data stream is actually ingested data streams to Lakehouse for analytic purpose. You can think about data streaming is where data is being originated, like they are generating from these business applications. They are used for intercommunication between microservices, maybe used for building out data pipelines and react to individual events. But all these data eventually goes to Lakehouse. And that means people end up building a bunch of bespoke integrations using connectors and converting the data from data streams to Lakehouse tables. and they need to deal with these complicated schema evolutions. So we kind of think take one step back and kind of think about if we already store data in certain format, which is already we already using S3 as object storage as a tier storage, originally as a tier storage, but why not we can just considering converting the data streams into Lakehouse tables. So then the data would be made available immediately for all the analytic processes in the lake houses for processing. So you don't need to do building additional integrations, pipelines to converting data streams to data lake. And that's very important thing for today's economic environment. Is everyone is thinking about cost. So if we can reduce remove the cost of our integration, that would be a huge cost saving for a lot of people. Although I think I want to add one more thing here, actually also about enable data sharing as well, is like the if you kind of looking what fundamental data streaming platform do is enable data sharing. They're just as what Matteo said, data streaming platform has been used for data integration across different surfaces, and we already did this in the more operational transactional world between a bunch of different real-time business applications. We would like to do the same thing for bridging the business application in an analytics process, and that's where making the data available as a lakehouse table is actually a big step to kind of fulfill our vision of enable data sharing across different teams, departments, and even organizations.
Thanks. I just wanted to get a little bit more clarification on why it's so important. I think it's clear to our viewers why it's so important that we support the Kafka protocol. But I wanted a little more context about why it was so important, why Lakehouse storage was so important, and what it enables our customers to do. And it sounds like cost savings and data sharing are the two real drivers of that.
Yeah.
So
exactly.
Thank you both for that introduction to Ursa, to understand what it is and why it's so important, especially in our cost-conscious streaming era. I'd like to actually go through a little bit of history, a little bit of history of Pulsar, and even before that, a little bit of history of Kafka and how times have changed since the Kafka protocol was first developed. Or I shouldn't say the Kafka protocol, Kafka in general was developed and why it's so important now as a protocol. So Kafka is obviously a dominant technology in the streaming market. And I'll say Kafka or Kafka protocol. When whoever answers this question, you can clarify which one you're answering to. But as mentioned, Ursa has near full support for that Kafka protocol. Maybe Sijie, if you can give me a little bit of background on the technology landscape at the time that Kafka was developed and why it was developed in the way it was at that time.
Sure. Like Matteo and I did a kind of presentation in the Pulsar Summit, and the way how we kind of view this is that we look back what's happening in the industry in the past 25 years. So if you're looking into the first 10 years from 2000 to 2010, it's mostly on-premise deployment where I think the network is very slow. So if you want to moving the tons of the data, it's almost impossible. So instead of moving data, you probably need to move the computation towards the data. And that's a lot of the data system has been architecting in optimizing the kind of a data, not to move the data. So that's what I think a lot of design is more kind of using computation and storage couple design. And one of the kind of a typical example in that time is Hadoop. And Hadoop is actually a big thing, is use these machines and optimize of the concept of moving data towards the computation nodes in order to kind of avoid moving data around through slow network. And Kafka is also almost built in around that time. Initially as an ingestion tool to get data into Hadoop. So it follow Hadoop's design principle to kind of using a coupled architecture. meaning putting all these kind of computation and storage node into as a one unit and serve from physical nodes, and that's the entire design being used in Kafka. But obviously, it's a great design in that time. But as the entire kind of the infrastructure has been shifted, moving from on-premise to cloud and cloud native from 2010 and to 2020, and that's where we kind of re-architect these to become Pulsar, which I think Matteo would have more words to kind of talk about that kind of entire story about creating Pulsar and how we leverage this containerized environment to bring architecture benefits to Pulsar. So, Matteo.
Sure. So when we get to Pulsar, essentially it was there are like the couple of different architectural traits, right? That were like designed to suit all the use cases we had we wanted to support in Yahoo initially. And the first design trait was around multi-tenancy, right? The realization about running a single service for the whole company instead of having each team to have to deploy their own messaging infrastructure. That was a huge win by having a single operational team, right? And then freeing every product team to build their own product instead of dealing with infrastructure and operations around it. The other design trait was on supporting messaging and streaming, and that's why we have support for queuing, messaging, and all these kind of use cases. Basically, we could replace in Yahoo all the messaging technologies from RabbitMQ, TIBCO, and Kafka, and other in-house streaming technology. So it was basically kind of like a catch-all for all kind of like data movement use cases solution. And finally, the coming from the multi-tenancy angle, right? You also had to kind of like design a system that can be scaled horizontally very efficiently, scale up and down, right? And that's when the separation of storage and serving from brokers and bookkeeper became very, very, very important, because if you have a single cluster, then you need to be able to expand capacity on a regular basis, right? And it is not something that you spin up a 3-node clusters and then you have your use case. It is pretty much static, and it goes on. If you had like hundreds of different teams using your service, your capacity will fluctuate, will get in onboard new users and so on. So having these separation of storage and compute and serving in this case was critical to achieve this kind of like level of availability and dynamic operations on the cluster.
At that point, it sounds like we have some background on why, or what were the principles that guided the development of Pulsar at Yahoo. And then that eventually brings us into the Pulsar being open sourced. So after being open source, if we skip a few steps, we eventually get to where we are. Not quite right now, because now we're in what might be StreamNative's Ursa era, but the beginning of the commercialization of Pulsar at StreamNative. So Pulsar's it's cloud native architecture. It's extremely scalable, highly available, very performant at low latency. Sijie, can you go over some of the guiding principles and more the key milestones that Pulsar has hit since it became open source? Like, what does that development cycle look like, or what does that development look like since it was open sourced?
Sure. I think the way since it's more kind of talking about StreamNative, and a lot of, I think we're probably going back into what is our product vision to a certain extent. I think cost is obviously everyone's top priority nowadays, but like almost every vendor jumping into the game of cost, like basically saying like X times cheaper, X times cost efficiency, and as a company, we are not shying away from kind of about this, talking about cost. Cost in a way is helping people reducing the total cost of ownership and bring value to the enterprises, which they can use the capital being saved from this infrastructure to do other business innovations and accelerate time to market. And in order to save the cost, I think architectural benefits like separating compute from storage to avoid over provisioning, saving data into a more cost-effective storage media is every step that we are taking to reduce the total cost of the ownership. But more importantly, I think there's a first principle that is kind of guiding us to achieve the cost effectively is how we can save one copy of the data and enable that same set of data being shared across different teams and different departments and even across organization. That is the first principle guiding us going through the entire journey of commercialized Pulsar to a certain extent. The Pulsar already have the unified what's called unified protocol, unified queuing and streaming that is built from early days. That is the concept behind unified queuing and streaming is essentially saving one copy of data and being consumed in many different ways to meet the business requirements. And this same principle is also kind of for us to building multi-tenancy. Multi-tenancy is a way that you just start one copy of data, being able to share with different teams within one cluster setup. So take that kind of into next step, essentially is that we instead of kind of creating a unified protocol, but we want to be making people be able to sharing between different protocols. And that's kind of we introducing the concept of KOP, start building out Kafka on StreamNative, and that's the evolution of the entire Kafka API compatibility leading towards to become the foundation of Ursa. That same principle is also guiding us to kind of consider, can we move the data towards more the tier storage? And that's why in 2018, I was late to 2018 or early 2019, we introduced the concept of tier storage. And that's actually taking the entire principle to another level, is that we can solve the data, make the data available in tier storage, and that is able to be maybe used for analytic purpose. And we take that into next step is to converting the data in tier storage to Lakehouse format, which is called nowadays known as Lakehouse storage, and that is kind of another involvement. For if you're looking back, all StreamNative does from funding towards now is with a mission is how we can enable data sharing across different teams, departments, and organization. And enable data sharing is actually reducing the entire cost of organization, because you can just save one copy of data and enable different teams to use the data via different protocol, different API, and different storage model. And that's kind of that is shaping the entire idea of Ursa. So I hope that kind of tie back a little bit on the product vision that we laid down there.
So it sounds like Ursa with Lakehouse storage is kind of the next iteration of cost savings, which is going to have a huge benefit. But in fact, cost savings has been a principle that's been around for a very long time in being able to have multi-tenancy and have multiple teams use a single cluster. That one cluster is completely elastic and scalable. Being multiple teams being able to use the cluster for messaging and streaming instead of having to spin up multiple clusters that have individual capabilities. All of these things all lead to cost savings. And Ursa and Lakehouse storage is just another iteration. It's the next major step in enabling our customers to be able to get more cost savings while sharing their data with more teams.
Exactly. Yeah. And one thing I want to also maybe call out from operational perspective, like I see many different vendors in the market is more looking into cost perspective, is looking how to, can I rewrite this in a different language? Can I re-architect or re-implement this in a different principle? But at the end of the day, I think the only principle I think guiding us from a product design perspective is how we can save one copy of data and use it multiple times, and that is the key to take the cost efficiency to an extreme. And another side, turning this around from operational perspective is you have different components. You want to make it using the what's available in the current environment and making sure the implementation fit into the current environment very well. And one example, obviously, is the Aksha. And I know there's a many like in the Kafka world, like people talking about implementing like a Kafka using K-Raft to a certain extent is actually a re-implementation of Zookeeper using a Raft algorithm, but it doesn't solve the fundamental operational pain points because you still need to running like 3 separate nodes, like forming as a K-Raft column, which exactly is Zookeeper is doing. Instead, I think the first principle that we have in building Pulsar kind of leading us to kind of really think the problem in a different way. And that's how we kind of coming up with a brand new kind of metadata management, metadata plan, which is like Aksha. And obviously, Matteo is the brain behind Aksha. I would let Matteo talk more about Aksha.
Actually, let me back up 1 second before we get Matteo to talk about Aksha. I think there is this, our viewers may hear some things that we are becoming keeperless, like Bookkeeper may be going away. But in fact, we'll get into that in the next, a little bit later. That Bookkeeper is not completely going away. It's still there if you want it. But but we're also removing Zookeeper. And Matteo, if you could talk a little bit about why we would even want to remove Zookeeper, and then how we basically fix the problem that Zookeeper had with Aksha.
Sure. So first of all, on the why, right? So we started with the realization that Zookeeper has been a limitation on the scalability of a single Pulsar cluster, as in that the amount of metadata you can store in Zookeeper, it is limited, right? In the order of 1 to 2 gigabytes. After that, it becomes unmanageable. It becomes too much because every node has all the same has to have all the same data. It is all kept in memory. There's a lot of storage related reason why it is not a good idea to store more than that. And because of that, you cannot have many topics. Also, you cannot scale the throughput of a single Zookeeper cluster, right? So the amount of write and read operation you can do on a Zookeeper cluster, it is limited by the capacity of the nodes, and you cannot add more nodes to have more throughput or more capacity. That's not how Zookeeper was designed. So when we first started looking into this was, let's try to design, and again, one step back here is Pulsar uses Zookeeper as for kind of like a dual purpose, right? One is metadata, which is, I know is a bit vague as a term, but in general, you can see metadata as pointers to data or like information that you need.
People might ask, why do we have 2 gigs of metadata? What is this metadata? Why is there so much?
Yeah, so I mean, if you have millions of topics, then it's even a small amount of pointers per each of these topics amounts to a whole bunch of aggregate size, right? And that's when you start hitting those limitations. So metadata is one. Let's say pointers to data, like where is my data physically located and so on. How can I retrieve it back? And that we need internally. And the other one is coordination, right? Zookeeper is designed for coordination. So in both cases, we'll say, okay, let's design a system that is best suited for everything we need. And since we can start from scratch with a fresh paper, let's design it right, what we need, and give up what we don't need, right? And for example, like Zookeeper has this property of global linearizable history. That means that every single transaction that gets applied on Zookeeper on different keys, you have a single history. But we don't care about it. We don't need it. So we don't want to pay the price for it, right? So we designed Oxytube to be horizontally scalable so that we can add more nodes dynamically, like auto scaling the cluster size based on the actual current traffic. And it is also sharded so that we can have multiple shards and have, probably you could have, say, 6 Octet servers serving like 10 partitions, and you can expand it to 10 Octet servers if the traffic rises, and then you can shrink it back to, say, 4 if the traffic goes down. So we designed against this requirement of large amount of metadata, and most importantly, expandable, right? That it doesn't have to be a huge cluster, but it can be a huge cluster if you have a huge need of metadata. And also that avoiding the storage inefficiencies of Zookeeper. Zookeeper basically has to dump the entire state every X amount of transactions. And if your state becomes bigger and bigger, then it doesn't really work well. So we have a much more sophisticated approach to how data is stored on disk because of that, and how quickly we can bring up new nodes, bootstrap them, and get them to be part of the cluster, and so on. So, and it is all. So the other thing is that the big difference is that it is expanded. So it is an architecture that is very different from what Zookeeper has. It is a stark contrast for what Kafka people did with Kraft. As Sijie mentioned, that Kraft is 100% the same architecture as Zookeeper. It is just put in a different place. Instead, we went opposite route. Here, we'd say, let's change the architecture to make it best work for everything we need to do. And the result is that we have a system that is much more elastic and that is designed to be deployed on Kubernetes. That's the primary environment design model. So Zookeeper was designed at a time where you have physical machines racked in the data centers. That's not the case anymore. Like, typically, we be running systems in Kubernetes in the cloud. So we take advantage of that environment that is not the bare metal machine environment. Instead, we can, by assuming Kubernetes environment, we can have a much simpler architecture, and we can have a much simpler implementation. So we don't have to implement Paxos or Raft or any of these protocols. Instead, we have implemented a much simpler replication protocol that is modeled after the Bookkeeper protocol, but it's a different implementation, but is like very similar in concept. That is much simpler to get it right. As you can see, that it took Kafka community, I think, 5 or 6 years before declaring Kraft GA. That's also because implementing Raft or Paxos protocol is complex and it is hard, and there are a lot of corner conditions. You have to handle all these corner cases. That's how it is. By choosing these, Kubernetes has the base environment. Our protocol, it is much lightweight, and it is easier to make it faster, because we don't have to handle a lot of corner cases.
What I'm really hearing is that Oxia was designed specifically for the exact needs of Pulsar. So that's why it's so great, really. Whereas Zookeeper was designed to be used for a lot of things, and we kind of used it until it didn't really work for us anymore. And Oxia is the solution that basically optimizes all of the metadata storage and serving for Pulsar, for the exact use cases of what Pulsar needs a metadata store. That's what I'm hearing.
Yes, and the realization is also that after we kind of started this and have the first version of Oxia out and so on, and we started finding new usages and new ideas on how can we leverage this technology, right? And the moment you have a fast access data that is strongly consistent, replicated, dynamically scalable, that has support for change data capture notifications to basically broadcast all changes and keep caches in sync. That becomes a very powerful abstraction, and we can add more and more use cases that can leverage this and make it to make our system more performance and easier to architect.
It sounds like it's good that we got rid of Zookeeper. That's great. We have Oxia now. I feel like sometimes when I hear some of the press releases, like I mentioned earlier, you might see that we're going keeperless. We're getting rid of Zookeeper and then getting rid of Bookkeeper. Some of our customers, or a lot of them, have come to rely on Bookkeeper as that extremely resilient storage layer. And Sijie, if I can just get you to describe what our Ursa direction really is to make sure that we let our customers know, let our podcast viewers know that they're not giving anything up with Ursa, because we're not actually getting rid of Bookkeeper.
Yeah, I think there's a lot of kind of to unpack with this no bookkeeper concept there. I think that to kind of really understand what's behind the concept of no bookkeeper, it's definitely it's a trade-off between latency and cost to a certain extent, and getting rid of bookkeeper from an operational perspective is actually making the entire system much lightweight, so you can easily run in a containerized environment. But obviously, in contrast, is in some of the workload, like Bookkeeper is actually a secret sauce to a certain extent, is how we achieve single-digit low latency in certain environment. That environment could be like a private cloud environment, or some of the public cloud environment doesn't need doesn't charge based on inter AG traffic. Most of the problem coming up, people hate data streaming system in a public cloud environment is the inter AG traffic. And so from that perspective, I think what we are not saying here is that we'll completely just remove Bookkeeper. We're just making Bookkeeper become optional. And then we give people options to trade off between latency optimized workloads versus cost optimized workloads. Because one of the strong reasons that we believe in here is that nowadays we're living in a much complicated and hybrid world. Not on-prem, solely on-prem, not solely cloud. We're actually in between. Some people move to the cloud. Some people actually reverse it and pull back and move all their workloads from cloud to their own data center. And some people need like single digital low latency. And some people want to give up the latency and more trade off the cost over latency. So that the fundamental kind of concept behind no bookkeeper is actually a trade-off. And we actually published a blog post talking about this new CAP theorem to explain the trade-off people need to kind of consider when choosing data streaming technology. Basically, you need to choose two between cost, performance, which is latency, and availability. So you cannot have two. You cannot have all three together. But the way how you can make it all three together is actually give people option. So you can choose what makes sense for your workloads and what makes sense in the environment. So if your workload needs low latency, if your workloads need low latency, or you are running in an environment that doesn't charge interzone traffic, like on-prem, private cloud, or some of the public cloud provider doesn't charge interzone traffic, you're perfectly fine to use Bookkeeper continually. It's the best secret sauce that we have as part of Pulsar. And if your workloads can tolerate much higher latency, and if you want to trade off cost over latency, then you have the option to choose a cost optimized like implementation that is based on object storage, and that's the kind of the concept behind no bookkeeper. And more importantly, I want to kind of also tie this back into Lakehouse. Is no matter which one you're choosing, whether it's a latency optimized or cost optimized, you have the option to kind of make the data stream being materialized as a Lakehouse table, and you have the ability to kind of make the data available for an analytic purpose. So that's the entire model behind no bookkeeper.
So it's not about removing Bookkeeper. It's about giving customers an option to remove it if they'd like, or is that there's the option of even storing some data in Bookkeeper and some in Lakehouse storage, depending on your use cases. You could choose which one you wanted, which data to go to.
Exactly. And I also want to probably emphasize this. We are able to do this is because Pulsar have a really great foundation. It's called multi-tenancy, meaning you don't need to. I see some of the vendors might be coming up with the similar idea, but they implement in a way is I give you a cluster that is purely optimized for latency. I give you another cluster purely optimized for cost. But in a large organization, you don't need to do this with StreamNative, with Ursa. It's actually you get a large cluster, and you can leverage the built-in multi-tenancy functionality to say, for this tenant, this type of workloads, I choose cost like latency optimized implementation, and for this tenancy, I use the cost optimized. It actually kind of perfectly fit into the entire multi-tenancy model that we have been built from day one.
It's been pretty clear to our viewers that you both have been thought leaders in the streaming space for quite some time, going back to the Yahoo days and actually creating Pulsar before it was open sourcing it, commercializing it, coming up with the cost optimizations that we've been talking about today. It's starting to feel like to me that Pulsar was actually kind of architected to be future-proof, that these different components are actually divided up and they can be replaced at will almost for whatever optimization you need. And it seems like this final optimization that you have here, or the most recent one, is not only optimizing for cost based on storage, but then subdividing that into tenants so that you can actually choose where different data is stored. This feels like if there's another iteration in the future that we have to optimize for something else, that you could re-optimize the architecture again easily. I'd like to get both of your thoughts on where that can ultimately end up. What if you take that thought process, and where does that leave Pulsar and StreamNative?
Matteo, you want to go first, or I can go first? Either way.
You can go first.
Yeah, so I think to answer that, I think technology is going to evolve like once a while. Almost every vendor try to kind of rewrite a piece of technology every while, because there's going to be evolvement from hardware perspective. There's going to be evolvement from economic perspective. But I think everything kind of pulling back is what is our vision and what is the first principle that we're following from day one. And actually, I think the vision we kind of laid down initially when we built out Pulsar and also found StreamNative is that how we can enable a platform that has the capability to enable data sharing across different teams and different departments or even different organizations. So we can share the data more effectively between services, between people, and between organizations. And in order to realize that vision, and also make it more cost-effective way, and there's always a kind of a first principle that we're following is saving the data only one time, or saving one copy of the data, use it multiple ways. And if you're kind of looking into the entire evolvement from Pulsar's unified meshing model towards multi-tenancy, towards this Lakehouse storage, we follow that first principle from day one till now, is try as much as we can to just save one copy of the data and use it in different way, having the ability to support different protocol and semantic to meet business requirements across the organization. So that's kind of the view. And even like in the future, in the like there's something new coming up, the entire infrastructure is being re-architected, we still probably be able to guide by this first principle to evolve Pulsar into the next generation to fit into that requirements there.
Matteo, any thoughts?
No, I agree that you always design for the current environment, right? Or where the trend is going, like what are the current concerns, and these are typically cyclical. Is like what is the bottleneck, CPU or memory, and you try to optimize for one of these. And in the data infrastructure environment, you have different constraints, which can be disk speed, disk throughput, network, cost of network. Like all these parameters are like volume of data that explodes suddenly and then drives like a whole bunch of re-architecture of systems, right? In general, there, if you start with the simple and elegant solutions and architecture, it is typically more easy to plug in different models and to adapt it. But instead of like if you have more something that is more tightly coupled with one particular environment, one particular architecture. So we try to be agnostic of the of that and try to design for more in a more general way, and understanding that the trade-off, that decision that we're making today might not be the same that we're going to make it tomorrow, and that has been true along the way from Pulsar, because we saw that in past systems that were designed for one particular environment, and then when that environment changed, they were not useful anymore, and then they had to be replaced completely and completely recreated from ground up and abandoned in a way. And because of that, we started designing with decoupling the storage and compute. Like once you have this kind of like abstraction, then it is much more easier to adapt to any sudden change or any like environments mutations.
Sounds great. That means whenever we have the next disruption, you guys will be able to re-architect again quickly to take it. We don't know what it would be. We're in the cost savings era right now, but there will be something else, and we should be able to re-architect it again when needed.
With minimal changes.
Yes. I want to thank both of you for taking time for the podcast today. And I guess what would be the call to action for anyone who wants to learn more about how to get started with StreamNative?
Yeah, I think StreamNative is available as like a fully hosted, and also we can do BYOC, and also if you want to self-manage yourself, there's a private cloud licenses available. If you want to try out piece of features like a Kafka API compatible, you can easily sign up StreamNative Cloud and start porting your Kafka application towards StreamNative. If you want to kind of more deploy in a more controlled environment, and also looking into more security related, you can also talk to us, contact us.
Sounds great. And thank you again, our viewers, for making it through the podcast. And that's all we have for today. Thank you so much.
Thank you, Dustin. Yeah.
Thank you, Dustin.
Follow the QR code on your screen to listen to all of the SweetStreams podcasts.